There are many standard examples of simultaneous move games with two players and two actions. In many real-world examples, we can expect that the number of players can be more than two. It is also possible to find many examples in which each player has more than two possible actions. Do either of these changes make it harder to find the pure strategy Nash equilibrium? The answer is that increasing the number of actions can make the exercise of finding the Nash equilibrium more tedious, but it is certainly not more complex. However, the task of finding the Nash equilibrium becomes more complex if the number of players increase. We will now consider an example with three players. Each matrix has two dimensions represented by the rows and the columns. With only two players, we used each dimension to represent the possible actions of each player. We can include the third player in two possible ways. One way is to describe a height of a matrix and say that the height represents the possible actions of the third player. This form of presentation is often not clear. The alternative is to present multiple matrices and map each matrix to a possible action of the third player. Let us consider an example. We consider a simultaneous move game with three forms. Each form decides whether to enter a market or to stay out. The payoffs are represented by the matrices you see. Player 1 chooses the row, player 2 chooses the column, and player 3 chooses the matrix. A common mistake is to think that there is something special about player 3. That is not right. Player 3 is not any more important than the others. We are simply allowing him to choose the matrix in which the outcome occurs. In each cell, the first entry is the payoff of form 1, the second entry is the payoff of form 2, and the third entry is the payoff of form 3. Let us consider an example to make sure we can read the payoffs properly. Suppose form 1 chooses to enter and the other forms choose to stay out. It means form 1 chooses the top row, form 2 chooses the right column, and form 3 chooses the right matrix. Hence, the outcome will occur at the top right cell of the right matrix. Therefore, form 1 will get -1 and forms 2 and 3 will get 0 each. Let us consider the best response function of form 1. This should tell us the best way form 1 should respond to any combination of strategies chosen by forms 2 and 3. Suppose form 2 and 3 both decide to enter. This means that form 2 chooses the left column and form 3 chooses the left matrix. Given their choices, form 1 knows that its choice is to get either -2 or 0. Therefore, form 1 decides to stay out because it prefers to have the 0. So I underline it. Next, suppose form 2 decides to stay out and form 3 decides to enter. Then form 1's choice is to get either 2 or 0. Therefore, form 1 decides to enter because it prefers to have 2. Likewise, we can find the best way form 1 can respond to any other combination of strategies of forms 2 and 3. These are all underlined. Hence, we have determined the best response function of form 1. We can similarly determine the best response function of form 2. Finally, consider the best response function of form 3. In this case also, we will find the best way form 3 can respond to any combination of actions of forms 1 and 2. Suppose form 1 and 2 both decide to enter. It means that the outcome will occur at one of the top left cells. If form 3 chooses the left matrix, then the outcome will occur at the top left cell of the left matrix, and form 3 will get -2. If, on the other hand, form 3 chooses the right matrix, the outcome will occur at the top left cell of the right matrix, and form 3 will get 0. Since form 3 prefers 0 over -2, therefore he will choose the right matrix. That is, he will choose to stay out. Now suppose form 1 stays out, but form 2 enters. Then the outcome will occur at either of the bottom left cells. By comparing form 3's payoff in the two bottom left cells, we know that his choice is to get either 2 or 0. Hence, form 3 decides to enter because he prefers 2 over 0. We can similarly find out form 3's best response for every combination of form 1 and 2 strategies. The best responses of form 3 are shown by underlining form 3's payoffs. We now check if there is any cell in which players play mutual best responses. There are 4 such cells, and these are circled. Hence, there are 4 pure strategy Nash equilibriums in the game. In 3 of them, one form stays out. There is also a 4th one in which all forms stay out.